Okay, so as promised, here's my video on max-min problems, finding the maximum or minimum, or they're called optimization because we're optimizing something, which typically it's the biggest or the smallest, right? That's what we want to optimize. What is the biggest or smallest solution? My favorite problem, because it's actually very practical, is making a can, and it's not one of the web assigns, but it should be because it's a classic problem. I think they probably did it in the book or something, like as an example, so they don't want to give it to you to do. But so let's do that example. Let's say you have a certain amount of metal. Let's make up a number. Let's say I have 100 centimeters squared of metal. Okay, so here's our example. You have 100 square centimeters of metal, and you want to make a cylindrical can to hold as many carrots or peas or whatever as possible, right? You want the biggest volume can you can make. So this is the surface area, right? So this is the surface area of the can, and you want to maximize the volume. You only have so much metal to make the biggest can possible, and basically the design of that can is what most cans are in the store because metal's expensive and whatever. So you want to maximize the volume. So what shape can, what shape radius, and everything else. So we don't even have to have a number here. We could just leave it as a value, and well, anyway, we'll figure it out. But let's start with the number. Makes it a little bit easier. All right, so that's the surface area. So first we draw a picture of the can, right, our typical can, and put some numbers on it. So we put a radius and a height, right? That's all you need for a cylinder is a radius and a height. And we know that the area is pi r squared plus pi r squared, so 2 pi r squared. So to do these problems, you got to know formulas for volumes of all different kinds of shapes. And you can usually look those up if you don't know them, right? But usually it's pretty easy. So 2 pi r squared plus the area of the can part. It's basically a rectangle, right? And the rectangle is circumference at the top. We cut the can down the middle and took the top and the bottom off, right? And folded it out. It's basically a rectangle where this is the height and this is 2 pi r, the circumference, right? The circumference is the width. So the area then is 2 pi r h, height times width, width times height. So that is the area of our can. That's, we know, is equal to 100 centimeters squared. We're going to really use centimeters for our units. So it's equal to 100. Okay, now the volume of a can is an easier formula. The volume is pi r squared h. It's always a base or top, whatever, times the height if it's a regular figure. You find the area of the base, and you just go up times the height. Any regular figure, that always works, base times the height. Okay, so pi r squared h. This is what we want to maximize. We want to take the derivative of the volume and set it equal to 0. But for these, as opposed to related rates, for these, we can't have two things we're taking the derivative of. We want to maximize it with respect to the radius or with respect to the height, not both at the same time. That doesn't work. So we need to get rid of either the r or the h, and that's what we use this equation for. This is the algebra part, right? It's geometry. With geometry now, as we wrote down these formulas, now the algebra part, we got to get rid of the h or the r squared. So we look up here, and which one is easier to solve for? And we only have the h once. So probably the h is easier to solve for. So we'll solve for the h, plug it in here. We'll have all r's. We take the derivative with respect to the r, find out what value of the radius is best, and then we can figure out what height is best because we'll have a formula for the height. Right? That's what we're going to look for right now. So we got to do the algebra for this, for the height. So let's see. So I'll just do that up here. So I have 2 pi r h equals 100 minus all this, minus 2 pi r squared. Divide everything by 2 pi r. So h is equal to 100 over 2 pi r minus, this is nice, the pi's cancel, right? I'll just show my work. Minus 2 pi r squared divided by 2 pi r. Or h is equal to, let's see, 100 divided by 2 is 50. So 50 over pi r minus, that's just r. That's nice. So we got to plug that in here. So that's equal to pi r squared times 50 over pi r minus r. Let's multiply that out. This is nice. The pi r squared cancels out the pi r in the bottom. We have 1r left over. So finally our volume then is, let's see, pi r, 50r, right, because r wins, pi r cancels out, yeah, 50r, minus pi r squared times r is minus pi r cubed. Okay, so that's the algebra part. Figuring out, getting only one variable, using this equation to get rid of the one. Now we can take the derivative, easy derivative. Take the derivative of this and we'll set it equal to 0. So dv dr, how it changes back to r, is 50 minus, see, 3 pi r squared. We want that equal to 0. So running out of room here, but I think I can do it. So we have 50 equals 3 pi r squared. R squared is equal to 50 over 3 pi. Now we can't have a negative r, right? That makes no sense. Of course, when we take the square root, we take the positive. So r is equal to the square root of 50 over 3 pi, which is a pretty ugly number. Now what is h? H is 50 over pi r minus r, which is a pretty ugly number. So let's actually get a value here, and because it's a little bit easier to deal with in dealing with all these square roots. So what would our radius be if we had 100 square centimeters? So 50 divided by 3 divided by pi equals 5.30. Oh, 5.30. So about 5.3. So this is equal to 5.3 centimeters. And now let's figure out our height, just because it's fun. 50 divided by pi r, 50, and r is 5.3, so plugging that in. So 50 divided by pi divided by 5.3 is, well, that's exactly 3, minus 5.3. So minus 5.3 is equal to about 2.297, and that's about 2.3. Is that right? So 2.3, yeah, about 2.3. So the height is 2.3. And that seems yeah, I guess so. Something seems off with that. So height is 50 r. Would that be right, that the radius is 5.3 but the height is only 2.3? I feel like it should be the other way around. So what did I do wrong here? 5.3, is that right? So 50 divided by 3 divided by pi. Aha! I knew that didn't make sense. I forgot to take the square root. Always a good chance to make sure they make sense. I knew something wasn't right. That didn't. Okay, which is 2.3. The square root is 2.3. So it's the other way around, it turns out. That one is 2.3. Okay, that makes more sense. 2.3 centimeters. Now if we plug in 2.3 there for the height, let me do that and see what we get. So, okay, yeah, I forgot to take the square root. Something's wrong. Okay, here we go. So 50 divided by pi divided by 2.3 is 6.919 minus 2.3 is 4.6. So the height is 4.6 centimeters, and it turns out, I knew that because I knew they would double each other, turns out the height is double the radius. Okay, that's the most ideal can, when the height is double the radius. So notice here, here's our height and there's the radius. So mine's a little bit too tall, right? Because if that's the radius, looks like it'd be a little bit shorter than that. But when the height, or basically when the diameter is equal to the height, that's the other way to look. When the diameter is equal to height, you have the most efficient can, which kind of makes sense. It's nice and symmetrical. Basically, the closest it is to a sphere, right? A sphere is the most efficient shape. So Okay, that's the idea with max-min problems. You've got to come up with the formulas using geometry or whatever, do some algebra, take the derivative, set it equal to 0, and solve for what values give you the best thing. So let's look at some WebAssign here now. Get rid of all this. Let's do a couple of those. And again, you can use, it's like related rate problems. Use geometry, use trigonometry, use Pythagorean theorem. You just kind of look at the situation and do the math and then take the derivative. But the key point here is you take the derivative and set it equal to 0. It's nothing to do with time. Time of the rates one, right? Related rates, how fast things are happening. This isn't how fast, just what is the shortest distance, the maximum distance, and things like that. Okay, so let's look at a couple of the ones in the WebAssign. Okay, so number 4, find two numbers whose difference is 152 and whose product is a minimum. Okay, so first off, we need letters for the numbers. Let's call them A and B. So difference is 152. So let's say B is bigger. Doesn't matter. B minus A is 152. Product is a minimum. Product is AB. We want to minimize AB. We want to take the derivative of AB and set it equal to 0. So we want to take the derivative of AB, set it equal to 0. But we have two letters there, right? We got to get rid of one of them, and that's what we use this formula for. A lot of times that's the way it works. You get two formulas, use one to get rid of the other one. So this is what we want to take the derivative of, set it equal to 0. So let's get rid of one of these. Let's get rid of the B, maybe, since we can write B is equal to 152 plus A. Let's change that. So this then is A times 152 plus A, which is 152A plus A squared. Now we can take the derivative of that with respect to A, because that's all we have. We don't have two things. So take the derivative of that with respect to A, that's super easy, right? The calculus in these problems is usually easy. Taking the derivatives is easy. The hard part, like the related rates, is setting it up. Setting it all up and getting ready. Taking the derivatives, usually they're easy derivatives. So this is the case here. So the derivative of this is 152 plus 2a. 152 a squared is 2a, and we set that equal to 0 to get a maximum or minimum. So let's see, 2a equals, did I just start? So b of 152, difference is 1b minus a is 152. Yeah, okay. So 2a is equal to negative 152. A is, what's 152 divided by 2? 76. Negative 76. I was thinking, wait, negative? Like, oh yeah, why can't it be negative? So I thought I made a mistake, but sure. So A is negative 76. What's B? So B is 152 plus negative 76, which is 76. Yeah, which is 76. So always check your answer. Does that work? The difference is 152. They're 152 apart. 76 and negative 76 are 152 apart. That works. And their product is a minimum. 76 times 76 is the smallest number where that can be the case. And you could try that, but I guess we'll just assume that. Now, how do we know this is a minimum and not a maximum? The derivative is 0 both places, right? How do we know it's a minimum and not a maximum? And that's where we can take the second derivative. So what is the second derivative here? So the derivative of, this is the derivative. We set it equal to 0. The second derivative of this is just 2. 2 is positive. That's the second derivative, right? It's always positive. So therefore, positive means that it's a minimum. If the second derivative is positive, it goes from negative slope to positive slope, so it's a minimum, right? It's a positive thing. It's a smiley face. It's a minimum. So we know it's a minimum. There is no maximum. Turns out there is no possible maximum. So we only get one answer. The answer can only be a minimum because the second derivative is 2. It's the same always. It's positive. We don't have an option. All right. So that's one example. Let's do one more here. And then I'll let you guys play with the other ones. Some of these get really hard. Of course, they start off with some easy ones. This one is like the one I did at the can. Okay, but now it's a box. It's got open top. If it's not an open top, the best box is a cube. Like symmetry is the best, like a sphere, like the can, the diameter is equal to the height. So they had to make it a little bit harder, and you take off one of the tops. So you find the area of, it's only one base, and then the four sides. It's a square base, so all the four sides are the same. You get formulas for all that stuff, just like the can one. I think you guys can do this one. Just remember it's an open top. The can, I didn't have to have an open top. It still makes it an interesting problem, but otherwise, you're going to get a cube. Okay, let's see. Find the point in the line that is closest to the origin. The point in the line closest. Okay, so now we have to use a distance formula. So we want to know the distance between 0, 0, and that line, right? So I don't know what that line looks like. Well, I can figure it out. See, when x is 0, it's 2, and the slope is 5, so it's something like this. So we want to know this distance here, right, where it's closest to the origin. So somewhere right in there. Okay, so what's the formula for the distance? We got to call that point something. AB is a good thing to call it. Let's call that point on the line AB. And we want to know how far AB is from 0, 0. So the distance formula, we could call it XY. I guess, why call it AB? Just call it XY. So we want to know the difference between X comma Y and 0, 0. So and X and then Y is 5X plus 2. So we can write our point as X and 5X plus 2, right? Because Y is 5X plus 2. Distance between 2 points is just the Pythagorean theorem. It's the distance between the two things. Since that's 0, it's easy. So X minus 0 squared plus Y, 5X plus 2 minus 0. It's nice that they said 0. They didn't have to. They could have said the point 1, 2, and then we would just put a 1 here and a 2 here or something, but they made it nice. Okay, so this is obviously just x squared, square root of x squared plus 5x plus 2 squared. Oh, that's terrible. Okay, it's not so bad. So it would be this squared plus that squared, 25x squared plus 2 squared is 4 plus 2 times and multiply together. Multiply together is 10x, so it'll be 20x. Okay, that is the distance. We want to, it's only an x because we got rid of the y by doing this, right? We want to minimize that. Take this, what is the smallest this can be? So first off, we can add those. Now here's the trick, right? We don't need to worry about the square root. All we got, if what's inside the square root is the smallest, then certainly the square root is the smallest. So we can just minimize without the square root. And we did this in pre-calc too. But in pre-calc, we had to have a parabola. Actually, it looks like we're going to have a parabola here. So actually, the cheating way to do this is to use negative b over 2a, find the vertex of the parabola. But the better way to do it is to take the derivative and set it equal to 0, because it's really easy to do. So add up all the x squared, so 26x squared. Take the derivative and set it equal to 0. And then find out what x is. And when you know what x is, you can know what y is, because y is 5x plus 2. Okay, so this one here, rectangle. Oh, yeah, let's do that number 7, and then I'll stop here. That'll be it. This one's a little bit, this is a fun one. Okay, so first off, we draw a picture because pictures help. So let's draw a picture here for number 7. So we have an ellipse, x squared over a. Now, right away, we know we're going to have an a and b in our answer. It's always actually really a good practice to put in a letter for a number, because then you can, after you get your formula, you can plug in any number you want. Otherwise, you wonder what happens to the numbers. So using letters instead gives you a general formula. Then after you're done, right, you can plug in a equals 3, b equals 4. Otherwise, you don't know how to do that. All right, so an ellipse is a stretched out circle. A tells you how much you're making it wider in this direction. B tells you how much you're making it wider, right? How much you're dilating it in the y direction. And this is equal to 1. So if both of those are 1, we have a circle. And it's not x minus 2 or y minus 2. So we know it's centered at the origin. So if a and b are 1, we have a circle centered at the origin. If a was like 2, then it's going to be stretched out twice as wide. So it's going to be something like this. Okay, so we're assuming that A is not 1, so it's interesting. And B is going to tell us how much bigger than 1 it is here. So if B was 2, this would be 2 high. Okay, so we want to inscribe a rectangle inside it. So what is the biggest rectangle we can put inside here? Okay, so given A and B or whatever numbers, there's certain numbers, what's the biggest rectangle we can put in there? I don't know. How do you do this, right? Oh my gosh. Okay, first off, one thing we can do to make it, I think this can make it a little easier, is by symmetry. Okay, this is centered at the origin, right? Again, like I said, there's no x minus 2, y plus 1. By symmetry, all we got to do is figure out one of these rectangles. The other ones, if I do the picture right, is all the same, right? They're all the same. So really, we only need to look at one of these. I think that makes it a little bit easier because let's look in the first quadrant. Everything's positive. Positive numbers are nice to deal with. So if we can maximize this rectangle, we certainly maximize the whole one because they're all the same. Okay. Because it's a nice symmetrical ellipse. All right, so that simplifies things for us. And let's see. We got to call our rectangle, put some numbers on it, right? So let's call this point here. We could call it AB. No, we don't want to call it AB because we have ABs there. That would be really bad. We could call it, we could just call it XY, I guess. Sometimes XY gets confusing because there's other X's and Y's, but so this point there is XY, which means that the area of that thing is X times Y, right? Because this is the height of the rectangle is the point, and the X value of the rectangle is the width. So there's the X value, there's the Y value of that point on the ellipse. So the area is XY. That's kind of nice. And we have this formula. So we have two formulas now. We want to maximize the area. We want to make that area as big as possible. So we want to take the derivative of the area and set it equal to 0. But again, my problem is I have an X and a Y. But I have this formula, so I have to solve for one of them to plug it into here to get rid of it. And then we take the derivative. Let's solve for Y so we have all X's because it's nice to take rid of X's. It's going to be a mess, right? So let's solve for Y here. So I have Y squared over B squared is equal to 1 minus X squared over A squared multiplied by B squared. Y squared is equal to B squared times 1 minus X squared over A squared. Take the square root. Now, when you take the square root, you get plus or minus, but for us, the Y is always positive, right? In this first quadrant, just one reason, nice way to do this. First quadrant, Y is only positive. It goes from 0 here to that actually, okay, we could actually say this point. This point is B, and this point is A. The biggest it can be is B up here, because that's the way this works. B tells you how much bigger it is than 1 in the Y direction. A tells you how much bigger it is than 1 in the X direction. So we can label those, but I don't know if we have to. Yeah, so take the square root. Y is equal to B. Square root of B squared is B times the square root of 1 minus X squared over A squared. No way to make that easier. All right, I can turn off the background here. I don't need to have all this light on. Makes it confusing. All right. We plug that into our formula now. So the area, which is XY, is X times that. So it's B times X times square root of 1 minus X squared over A squared. Okay, looks like we're going to have to use a product rule here to take the derivative with respect to X. So let's take the derivative. We can treat this like one thing and this like the other thing. So the derivative of A with respect to X is derivative of this, which is just B times the second, square root of 1 minus X squared over A squared, plus the first, bx, times the derivative of this, which is 1/2 1 minus X squared over A squared to the negative 1/2 times the derivative of what's inside. Can't forget the chain rule. Derivative of what's inside, that's 0, that's nice, but here it's negative, so 2x negative 2x over a squared. So times negative 2x over a squared. X squared is 2x negative, yep, that's right. That looks like a mess, but we can simplify it. Let's simplify it. Well, okay, we set this equal to 0 now. I'm going to have to work over here. So we set that equal to 0. So I have this side. Now this is negative, right? This is negative over here. So I put it on the other side, it's positive. And I'm going to do this right now. The 2's cancel. We have a 2 up here, and we have a 2 there. And we have an x and an x, and that's the square root at the bottom, so I'm going to just write it all like that. So on one side we have b square root of 1 minus x squared over a squared equals, on the other side we have x times x, bx squared over a squared, bx squared over a squared, and that square root is on the bottom. So really I should make mine, well, I'll just put it at the bottom, times the square root of 1 minus x squared over a squared. Because it's negative square root, right? Negative square root is the bottom. Okay, we can multiply the bottom over here times that one to get rid of the square root. How nice is that? That's oh, and the b's cancel. Look at that, the b cancels. And multiply the square root on both sides here. So we have 1 minus x squared over a squared, by multiplying both sides by the square root, right, is equal to, on the other side, we have x squared over a squared. So it sure looked like a mess, and look how nicely it simplifies. Now let's put this on the other side. So 1 is equal to, we have x squared over a squared plus x squared over a squared, which is 2x squareds over a squareds. What are we solving for? X. We want to know what x is. So multiply both sides by a squared over 2. That gets rid of that. So we have x squared is equal to a squared over 2, or x is equal to, and again, we're only dealing with the positive thing here, so we don't need a plus or minus, this would be plus. So there's a square root of that, which is a over root 2. What a wonderful answer. A over root 2. We want our x to be whatever the a value was in our original formula times divided by the square root of 2. Now, what is y? So y is this. We got to plug our x into this to get y. My guess is it's going to be b over root 2. Like symmetry, right? Why should it be different? But let's try it out. So here's our y. So y is equal to b square root of 1 minus x is this. So x squared is a squared over 2. So x squared is a squared over 2 times, oh, and then x squared is a squared over 2 divided by a squared. Look at that. The a's cancel. 1 minus 1/2 is 1/2. So that's b times the square root of 1/2, which is b over root 2. So yes, it makes sense. So that is the area for this little rectangle. And I don't even know what they're asking. So now we got to make sure we're asking the right question. So what do they want to know? We'll find the area of the largest rectangle that can be described. Okay, so the area of our rectangle is xy. The largest rectangle is 4 times that. So we just got to multiply the answer by 4. So what is the area? Okay, the area is, hit the wrong button. Okay, the area is x times y. So that up here, area is xy, which is a over root 2 times b over root 2. Oh, times 4. Because we have 4 of the rectangles, the little ones there. So the area is 4x. The total area is 4xy, which is 4 times that, which is just a 2 in the bottom. So 4ab divided by 2, or it's just 2 times ab. Wow, that's a cool answer. 2ab. So whatever a is, whatever b is, it's just 2. See, and now we can say, okay, let's make a 3 and b 4. The area now would be, we know exactly what it is. If we had put numbers in, we would have had to do it all over again, because who knows what would have happened to the numbers. So by leaving it as variables, as a and b, we can now have a general formula, So now we can do whatever a, b we want, and we know the area of the biggest rectangle inside. 2 times a times b. Pretty sweet. Okay, hopefully that can get you started now. The whole idea again is you use geometry, you use Pythagorean theorems, you use circle formulas, ellipse formulas. Many times you get 2 formulas, you solve for one, put it in the other to get rid of one of the variables. Maybe that's all the time you do that. Maybe that's the way you do it all the time, because you can only take the derivative with one of them. You only got all x's or all y's, or whatever. And then you take the derivative set equal to 0 and solve for the value that gives you that. Okay, good. So good luck on these, and we'll go over them again on Tuesday. And yeah, okay, good. Oh, 30 minutes, not too bad. Bye.